Welcome back. Welcome back to ECE 207. Need to make sure that I'm turned on. Apparently by the conversation in the room, you guys are turned on, which is good. What a difference a week makes, right? Today for announcements, homework 1 is due on Thursday. That should be on the website, the D2L website, that particular assignment. Today what we want to do is start Chapter 2 material. This is not all of Chapter 2, but I've simply highlighted Chapter 2, meaning you need to be reading that if you haven't already started. Today we'll start with combining resistors. If we have a collection of resistors in series or in parallel, how are those combined? Then we will look at a particular example of how we might use that analysis, or actually this is a little bit more difficult than series and parallel. We'll see if we can understand how to compute the equivalent resistance for an infinite ladder circuit. That hopefully will become clear as we work through that or introduce that problem. We'll then show why this is useful in terms of being able to combine resistors, parallel combinations, series combinations, etc., to help us analyze a circuit differently than maybe KVL and KCL, which is what you're doing in Chapter 1 type material. Then we might have a class participation problem on voltage divider and current divider. Everybody opens their books and starts studying for that and misses the rest of the lecture. Hopefully that's not the case. Okay. Let's get started then with Chapter 2 material. Which is resistive circuits. In particular, let's start this first piece by looking at how we might combine series and parallel resistors, or what happens when you have a collection of resistors in series or if you have a collection in parallel. Can you simplify those down into an equivalent resistor? For series resistors, what we're really wanting to do is replace one circuit diagram with another. Suppose we have the following circuit. A voltage source in series with 4 resistors. We don't yet know what those values are. That's not important for this discussion. Those are all in series because they carry the same current. The same current is flowing through all 5 elements, 4 of those elements being resistors. We want to know if this is now, we'll call this circuit A, can we replace that or replace A with an equivalent circuit which I might refer to as circuit B. Same source, but now we're consolidating or collecting or somehow grouping all of those individual resistors, R1, R sub 2, R sub 3, and R sub 4, into an equivalent resistor, a single resistor, which we're labeling R equivalent. Another way of phrasing that would be, what is R equivalent in terms of R1 through R sub 4. If you go back and look at those circuits and start thinking about how you would have analyzed those using Chapter 1 techniques, you might be interested in the current that's flowing in those circuits. And if they're equivalent, or if our replacement resistor, R equivalent, can be considered equivalent to the other four, then what we would like to think is that this current flowing in both circuits is the same. Obviously, we would want that current to be flowing in the same direction. If R equivalent is equivalent, or let's say is to be equivalent, the current in both circuits, or I sub s, must be the same in both circuits. If that's the case, let's go ahead and analyze both of those circuits. Suppose we do a KVL in circuit A. And if you're remembering what we had done last week, we might define that as a single mesh, where that dashed line is now a mesh that we are going to travel as we go through those different elements and sum up those elements. Once we get back or return to this place that we started, that sum should equal 0. Similarly over here, when we get to circuit B. In circuit A, if we call that, let's say, mesh 1, we could say we're going into the negative terminal of our voltage source. That's minus V sub s. Then we have the drops associated with all of those resistors. We have Ri across R sub 1, which is R sub 1 I sub s, plus R sub 2 I sub s, plus R sub 3 I sub s, plus R sub 4 I sub s, and those need to sum to 0. Or we could write that as V sub s, moving V sub s to the other side, and I'm actually then just rewriting it with V sub s on the left. V sub s becomes equal to, and let me factor out the common variable in the resistor terms. We then have the sum of those resistors all multiplied by the current going through those resistors. If we do the same kind of analysis in circuit B, then we can see that we have minus V sub s plus R equivalent I sub s is equal to 0. Or, rewriting that in a structure similar to the earlier equation, or circuit A, we see that V sub s is now equal to R equivalent I sub s. What we want to do now is, if R equivalent is the same as those 4 resistors, we can compare the parenthetical terms and see that R equivalent for a collection of resistors in series is just the sum of those resistors. And that was maybe already what you expected. So by comparing those equations, that implies that R equivalent and you don't have to put those out of order. I'm not sure why I did, just to see if you were still awake. You can number yours numerically 1, 2, 3, and 4. Or you could say that series resistors add. If you have a collection of resistors in series, you can add those up and replace those with an equivalent resistor if that will help simplify your analysis. Let's look at what happens with parallel resistors. Using the same strategy, but now we have a slightly different circuit or set of circuits. Let's call this circuit A, and let's again say that we want to replace circuit A with circuit B, where circuit B has been simplified to have an equivalent resistor. And hopefully you know that this R equivalent, we've now erased the earlier one. This is not the same resistor necessarily as what we had in the last example when they were in series. If we're doing that, the reason these resistors are in parallel is because they all share the same voltage. If you look at the different points, here are the two endpoints of resistor 1. That is the same set of points on R sub 2 electrically. Likewise for R sub 3 and R sub 4. How would we analyze circuit A based on chapter 1 type analysis? Or what's the unknown that you might be after? If somebody said solve circuit A, what would you be looking for in order to have all the answers? You know the source. Oh, another question that I had today in office hours is, what is a current source? It's maybe more intuitive. We've grown up with batteries. A battery is pretty clear. Here's a battery. I know what that is. It's either a 9-volt battery, it's a AA, it's 1.5 volts. It's a car battery, it's 12 volts. What does that mean? That means that ideally, whatever you hook up to that battery, it's going to supply or deliver 12 volts, 1.5 volts, 9 volts. It will always give you that. That's an ideal battery. Obviously, batteries wear out and the voltage drops. But for this ideal source that we just drew with the plus and minus sign, that was an ideal source. And that's going to be V sub S, whatever we specify V sub S is, and whatever we hang on the end of it, that's going to deliver that voltage. Likewise for a current source. This current source that has an arrow in it, it's going to deliver a current, whatever that current is specified to be. If that current source is a 1 amp source, no matter what you hang on the other side of it, it's going to supply 1 amp. The voltage might be 20 volts, it might be 2 volts. It's always going to deliver 1 amp. Or maybe it's going to be a sinusoidal current source and it will be going up and down as a sine wave. Yes, sir?
Is there a voltage drop across it? Like if we did KVL, would you just do nothing there?
So the question is, what if we tried to do KVL with a current source? We don't know what that voltage is going to be, do we? Because it's going to be whatever it needs to be in order to satisfy the specification of that source. So we can't necessarily go up and say, oh, well, let's just do the voltage drop across that source. We don't know what it's going to be. So you don't do drops across the voltage source. Just like you don't do currents in or out of a voltage source. Did I say that wrong? Current source, you can't do KVL. Voltage source, you don't really do KCL with. You don't know what the current is. The current's going to be what it's going to be for a voltage source. For a current source, it's going to deliver the current that's specified, and whatever that demands for the voltage is whatever it is.
But there is some voltage.
But there is some voltage. Why is there some voltage? Because it has to be supplying power to your circuit. So you know it is going to give you a voltage, but you don't know necessarily what it's going to be. Because the product of voltage and current gives us the power. And if it just keeps operating and operating and operating, that's going to give us some energy. Question?
Why did you use a current source instead of a voltage source this time?
The question was, why did I use a current source instead of a voltage source? Because it makes the analysis easier. But it really helps me illustrate the point. If I put a voltage, actually it makes the example more meaningful. If I put a voltage source across that, everything is in parallel and everything would have that same voltage. And really there wouldn't be a problem, is what I would hope. On exam 1, if I messed up and gave you that problem and I ask you, oh, what's the current through R sub 2? And I actually put a voltage source there, that would be like a gift, I think, because you know the relationship between current and voltage on a resistor. V is equal to IR. If I gave you, instead of that current source, if I gave you a voltage source, there really shouldn't be much to do. You have the current through R sub 2 would be that voltage divided by R sub 2. So it'd be pretty easy. This makes it a little more interesting or challenging. You don't know right off the bat what that voltage is across R1, R2, R3, and R4, although it is the same voltage. Does that make sense? Which leads us to my earlier question. What are we interested in? Yes, if we had the voltage, we would be done. And how many voltages are there in that circuit? There's really only one that's unique. Correct? You have, how many nodes do you have in that circuit? In circuit A? Do you have all of those dots or those nodes? Mechanical drawing, yes, maybe they're a node, but electrically those are all this. 4 of those are the same. Here's one node. And there's the other node. And typically we use the bottom node as our reference node, and we will reference the voltages relative to that bottom node. Meaning, if we can now identify that voltage, let's say it's V sub 1, that V sub 1 voltage is the same across R1, R2, R3, R4, and across the current source. It's the same voltage. Likewise over here. We have 2 nodes. How are we going to find, and this voltage, if these are equivalent, whoops, that should have been I sub S. Hopefully you weren't asleep and you wrote that down. I'm up here sleeping. Occasionally you'll have to shake me to wake me up. I can walk around, I can sleepwalk. And you guys probably do that too, right? You come to class. Weren't you in class the other day? Yeah. Were you awake? No. Your eyes were open. That's what happens after 2 years of school, right? Don't have to shut your eyes to sleep. Where were we? Trying to solve for V sub 1. How do we solve V sub 1? KCL. We need to find the currents coming out of that top node. So if we do that, in circuit A, we could write that in the following way. And there are a lot of different ways to do that. But suppose I say I sub S is going to go into that node, and all the other currents going through those resistors are coming down, and they're going out of that node. So those will equal I sub S. The current going through R1 is V1 over R1. The current going through R sub 2, same voltage, different resistor. Current through R sub 3, V1 over R sub 3. And that's just the voltage-current relationship of a resistor, written in terms of solving for the current, plus V1 over R sub 4. Is it clear where that came from? Now let's pull out the common variable. If we knew the current source's value, and if we knew all of those R's, we could find their inverses, sum up the inverses, divide that out, and we could solve for V sub 1. That's the only unknown in that circuit. But what we're wanting to do is find out the relationship between this resistor, R equivalent, and these four resistors, R1 through R sub 4. We'll do that doing the same analysis with circuit B. In circuit B, it's maybe too easy that we make it hard, but in this case, I sub S is V1 over that single resistor, R equivalent. And if I write that similarly to how I wrote the earlier one, or circuit A's relationship, I now have I sub S is equal to this quantity, 1 over R equivalent, times the voltage V1. If those are equivalent circuits, V1 has to be the same in both. And that now gives us our relationship that we were after to relate resistors in parallel. We now know that 1 over the equivalent resistor is just the sum of the reciprocals of all of the resistors that are connected in parallel. And you may not see it written in that form, but you could solve this for R equivalent by simply taking the reciprocal of the right-hand side, or the inverse. And we now have R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. If you have resistors in parallel, you then need to use this formula, which is 1 over the sum of the reciprocals of those resistors that are in parallel. And we tried to show why that's the relationship that holds, or is true. It's nice to actually have this for a particular case, which is for 2 resistors. And that is, if we wanted to replace these two resistors that are in parallel with each other with one resistor. That's what I'm meaning by R equivalent, looking into these two terminals or nodes. If I attached my multimeter to those two nodes, what would I measure? It would be related to R1 and R2. And in particular, in this case, if we use the formula, it would be 1 over R1 plus 1 over R2. But you may not see it written that way, and that's why you learned algebra in second grade. So you could simplify this, right? Or whenever you had algebra. Maybe you had it in kindergarten. I was still painting finger paints with my fingers in kindergarten, but you guys were probably well beyond that. They push you guys really hard, right? So you were doing algebra in grade school. How do we do that? Let's get a common denominator in the denominator. And now we can multiply by 1, which is R1, R2 over R1, R2, and that will then effectively flip upstairs. And let me write the denominator sum sequentially so that I now have the product divided by the sum of those two resistors. And that's a convenient formula that you might want to just commit to memory for as long as you need it. But what does that mean? If somebody has a circuit and they say, oh, here's R1 and here's R2, I'm going to replace that with an equivalent resistor. You can't see this. I'm on audio, not video, so I can be wherever I want, right? What if I had a 10 ohm in parallel with another 10 ohm resistor, and somebody said, oh, the equivalent resistance is 12. I'm seeing some heads going left and right. Did I see any going up and down? In some cultures, this means no, I think. So I never know if I'm seeing the right symbol or not. But resistors in parallel, you should end up with something less than any of them. If you have two that are identical, you're actually going to split those in half, and that will be your equivalent resistor. If you have an R1 and an R2 of 10, you can see that you have 10 times 10, 100, divided by 20, or 5. So you did split it in half, and that's consistent with what you would get for any identical two resistors. In parallel, you'll just split them. And you'll end up then with the combination being half of what you started with. Questions on combining resistors, series and parallel? Let's then look at a particular problem. Problem 9 in Chapter 2, which says to find the resistance looking into those two terminals. And these resistors are 1 ohm. Well, it's surely not that easy. And it's not. Suppose we add some more. It's not that easy. You know what? Just keep that pattern going forever. Is this south? I'm so turned around in here. That. All right. That's east? Really? Okay, if we just kept going to New York City, we're still attaching resistors in this same pattern. And I want to know what's the equivalent resistance measured with that ohm meter. What am I going to see on that dial if I just keep building on? If you use your imagination, you can maybe see that as a ladder on its side. If you were to, here, let me turn that right side up. Sorry, that wasn't funny, was it? If you turn that circuit 90 degrees, hopefully you can see that that looks sort of like a ladder. That's a ladder network, is what it could be called. You're making that ladder infinitely long. And you want to know, if you measured it, what would that be? Now, if I had a ladder, I would go up and cover up the right-hand side of that, or the west end of that, if we're in the right. I would cover it up here, but that wouldn't make any difference, would it? If it was on the Elmo, maybe it would. Sorry. But if we had that circuit that I had before, the very first one I drew, 2 horizontal resistors and 1 vertical, what would the R equivalent be? If I erased everything but the first 3 resistors that I drew, what would R equivalent be? 3. How much do you think it's going to be? Greater or less than 3? If you're doing this and you come up with an answer and it's greater than 3 or less than 3, which one would you have a more warm, fuzzy feeling about? Less than 3, based on what we just said about combining things in parallel, because you're now really sort of hanging another set of objects in parallel onto that particular point. So you're somehow lowering that 1 ohm resistor with more pieces. But you still maintain those first 2, or the horizontal 2. So maybe you're expecting something between 2 and 3. Correct? I mean, if you really thought that that's going to really reduce things between the red or the blue nodes, you would say, oh, well, the ultimate would be that goes to 0. If that's now 0, those 2 blue dots become 1, and you have 2 ohms across the red dots, right? So now we have a feel for where the answer should be, between 2 and 3. Maybe. Yes? No? With that logic, let's see if we can reason this out. That particular circuit that I now have drawn should be or let's just assume that it is equivalent to the following. It's now equivalent to, here's 1, 1, 1, but now I'm going to attach that and if it's semi-infinite, that R equivalent should be equivalent to all of that other piece, that other structure, and that structure could go on forever. But that is supposed to be the same as R equivalent. Right? It doesn't really matter if I keep adding sections. That's supposed to be equivalent. Let's see if we can write an equation that describes this relationship. Can I? Can I write a formula for the green R equivalent in terms of 1s and the red R equivalent, where the green and the red are actually the same? What would be my equation? Here's the green. R equivalent is equal to, it's this plus that. Yes? So it's 1 plus 1. I'm afraid to write what that curly brace means. What's in the curly brace, or what's that resistor? That's two resistors in parallel, isn't it? And we just derived that relationship. That was the product of the two, 1 times R equivalent, over the sum of the two. Is that okay? Now it's a good thing we know our algebra. That's all we're going to do. Let's see if we can find an equation that R equivalent must satisfy. There's a 2. If I collect my 1s, here's R equivalent. That's 2 plus R equivalent over 1 plus R equivalent. If I put those over a common denominator, having trouble with my Q. If I do that, I now have 2 times that denominator, which gives me 2 plus 2 R equivalent, but I also have that other R equivalent. So 2 plus 1 R equivalents gives me 3 R equivalents. Is that okay? Or I now have this equaling that. Let me clear my fractions. Let me multiply both sides by the denominator, 1 plus R equivalent. If I do that, I end up with R equivalent plus R equivalent squared is equal to 2 plus 3 R equivalent. Make sure I'm still awake. Is that okay? Question? So the reason you're still stuck on why I said they were equivalent, right? Yeah. So the question is, in the original drawing, how come you could conclude that those were equivalent? And yes, your question or phrasing is the correct answer. They're equivalent because it doesn't matter if you add another 3 resistors on to the right-hand side, you're not going to change anything because it's infinitely long. And so infinite plus 1 is what? Infinite plus 2, infinite. So we're assuming it goes on and on for infinity, and so it doesn't matter. That's why if we added another piece onto the left-hand side with the same structure, that looking in is going to be R equivalent. That being the case allowed us to derive this relationship for R equivalent. Did that sort of answer your question? I think you knew what it was supposed to be. You were just questioning whether or not that was indeed what it was. But yes, that's what it is. Now we have a quadratic. Let's bring everything over to the left. And you can now go home for the Labor Day weekend and say, Mom, Dad, this is why I bought my $200 calculator, so I could solve these quadratic equations in 207. Okay, I believe that. Maybe that wasn't. How do we do this? The quadratic formula. Negative b, which in this case is minus 2, minus a minus 2, so we get 2 plus and minus b squared minus 4 times AC. A is 1, C is minus 2, and so that gives us plus 8. 2 times 4 divided by 2A, and A was 1. Or this now becomes 1 plus and minus square root of 12 over 2. Where did that 2 come from? Oh, of course. It was in the denominator. I should have known. Now if I draw it back, will it appear somewhere else? Are you guys paying attention to this magic that's going on in front of you? Stay, boy. Good. Square root of 12. 4's in there, isn't it? And we can pull out the square root of 4, which is 2. That gets rid of the denominator. And we now have 1 plus and minus square root of 3. And the square root of 3, isn't it 1.73? Does somebody have that memorized to 50 digits? Oh, thank you. I don't. I don't need you to know it for more than a couple. Is that what we were guessing our resistance might be? Somewhere between 2 and 3? And it is, isn't it? It's between 2 and 3. So that satisfies our suspicion, our warm fuzzy feeling that that is the right answer. So if we put an ohm meter on that infinite ladder network, it would measure 2.7 volt, 2.7 ohms. Questions?
I don't understand if you're making the whole system, like you're saying the equivalent resistance of the infinite minus 1 is the same as the resistance of the whole thing, but then like you're working with infinities as if they're regular numbers and then getting a regular answer.
Did everyone understand that question? I can appreciate the question. I'm not sure that I know how to rephrase it. I don't know even where I went to with that. Probably the same place that the 2 went. You have to be patient. This is a review. For the next 30 seconds, this is only a review. There. If you just keep hanging more and more elements on to the right-hand side, then all we are saying is it really doesn't matter once you get far enough out there to the right, all of this is going to be the same as if we erased those first 3 resistors and looked only into here. From the blue, or if we looked into those nodes, we would see the same resistance. If we see the same resistance looking in to those black nodes as you see from the red nodes, and the reason, and the reason that's true is because it's infinite in extent, then we can say that this resistance between the black nodes is our equivalent. So you just kind of have to start to feel comfortable with that. And what you could do is just stop it at a finite number and see what you get add some more, and eventually you're not going to change the significant digits very much as you add more and more. And you'll say, that's fine. It's 1.732. That's good enough. Okay? So you just kind of have to look at it and think about it, but we're saying that going into the black nodes, if you erased or removed those front three on the left, you would get the same R equivalent as if you added those three on the front, on the left side, and measured R equivalent again to the significant digits that you're after. Question?
So could we draw the box like one set over, like to the right, and come up with a relationship like we did and get that same number?
So if you drew your dashed black line one, let's say, vertical resistor to the right, and did the analysis, well, maybe we'll take out a piece of paper and see, right? So the question was, if we did some analysis on that, would we get the same answer? The theoretical answer is yes. Whether or not we would with the analysis is another question, but it would make the analysis just a little bit more difficult.
Because that would prove it.
And that would verify, so you could sort of prove it inductively, would be that particular approach. You could say, okay, it's true for 1. Let's show that it's true for n. Now is it true for n plus 1? And then we could say, okay, we believe you. It's a proof now. I sort of did it by saying, please believe me, that this is the same as that, and then go from there. Other questions? Let's now use these tools that we've developed which are how we combine series and parallel combinations of resistors to help us solve circuits. The idea behind this is the following. We want to collapse everything down, simplify things down, try to get an answer, and then start growing back to the original and start seeing if we can get answers that we need as we expand the circuit back after collapsing it. Problem 24 in Chapter 2. We have a circuit. What's that element? Current source. That's going to supply 2 amps no matter what you hang on to it. That's an ideal source. Here's a 12 ohm, a 24 ohm. I'm going to forget the ohms. Here's a 6 ohm, 12 ohm, 8 ohm. And the problem asks you to find that voltage drop. So there is a voltage drop across a current source. Find this current flowing up in through that 12 ohm resistor. That's I sub 1. And find this current flowing through the rightmost resistor, the 12 ohm on the right. That's I sub 2. Find I1, I2, and V. just as you're thinking about this problem. You have a 12 ohm on the left, a 12 ohm on the right, and you're asking for the currents through those. Do you think the currents are the same? No, they're in different directions. Okay, yes, that's correct. One's up and one's down. So that would be correct. But are they the same magnitude? That's what you want to start thinking about. Are they? Now, if the right side looked like the left side, that 8 ohm is in the center, so it can kind of say, oh, it's not really impacting the right or the left. It's equally impacting those. But on the left, you have 12 and 24 in parallel, and on the right, you have a 6 and a 12 in parallel. So they're probably not both sides pulling exactly the same current, are they? What we're going to do is we're going to initially collapse those two parallel combinations on the right and the left into one resistor. The idea is to now really just get 3 resistors in series. And if we have 3 resistors in series, we can add all those up, and now we just have one resistor with 2 amps going through it. And if we know the resistance and the current, we can find the voltage, and that will give us our voltage dropped across that source. That's the concept. Once we have the voltage dropped across there, we can start pulling our way out from that condensed circuit. Let's start by combining the parallel resistors. And I sub 2, I'm going to call those R sub 2 equivalent on the right-hand side. And because I1 is on the left, I'm going to call that combination of 12 and 24 in parallel. Those are going to be R sub 1 equivalent. R sub 2 equivalent is the product of those two divided by their sum. Those are the 2 resistors on the right that are in parallel. And I can do some of that. There's 18, this 18. And now I have 12 divided by 3, or 4 ohms. Does that make sense? 6 and 12 in parallel, and I said the combination has to be less than the smallest. The smallest was 6. You would expect a resistance smaller than 6. And it is. 4 is smaller than 6, so that seems to make sense. How about the next R equivalent, which was R sub 1 equivalent? That was a 12 ohm in parallel with a 24. There's 36 in the denominator. Now I have 24 divided by 3, or 8 ohms. And 8's less than 12 and 20. Well, it's less than the smallest, which was 12. That seems to make sense. Let's redraw the circuit. We now have the circuit looking like the following. There's our 2 amp source. We have now replaced the rightmost, which we were calling R sub 2 equivalent. That's now a 4 ohm. We didn't touch the middle. And the left was the parallel combination of 12 and 24, which is 8. Let's see if we can find that voltage. Or we could fairly quickly say, let's go ahead and combine those R's which are in series. Same currents going through all of those, or the series equivalent is 4 plus 8 plus 8, or 20 ohms. Now our circuit looks like that. And the voltage dropped. If we put a voltmeter across that current source, it's across the resistor in the same orientation. We're just measuring the voltage drop across that 20 ohm resistor, with the positive terminal on the right, the negative terminal on the left. And what is that voltage? That current now goes in the positive terminal, which is the passive sign convention. It's R times I. R is 20, I is 2. V, one of the unknowns that we were asked to find, is 40 volts. Now we can expand from that to try to find the currents on either side. The right side was I sub 2, the left side was I sub 1, I believe. But to find those, it'd be nice if we knew the voltage drop across those two resistors on either side. If we know the voltage drop out there, then we can find the current for either of those resistors. Meaning, let's now look at this circuit. This one was 8, this was 8, and this was 4, and this is 2. If my current is going that way in a clockwise direction around that mesh, I could say, well, let's call this V sub 4 because of the 4 ohm resistor, positive to negative. This I could say, let's call that V sub 8. How would you label the 8 ohm resistor on the left? You wouldn't. You would just leave it blank and hope the grader missed it. What? V sub prime 8? How about just V sub 8? Isn't it going to be the same voltage as across the other 8 ohm resistor? Current's in the same direction. If I label it now plus to minus, if the current is going in that direction through that 8 ohm resistor on the left, it's going to be the same voltage as in the bottom resistor from right to left as from bottom to top. Is that okay? So if I find one of those V sub 8s, does anybody have a V8? I'm sorry. You guys could have had a V8. Oh, that was a subscript, wasn't it? V sub 8. Sorry. V sub 4. Do they even sell that anymore with all these energy drinks? You probably don't need a V8 anymore, do you? That's old school. Too much acid and not enough caffeine, is that what that one would be? V sub 4, what's that? If you forget everything, you should know Ri. And now you just need to make R the correct R and the I the right I. What is R? That's 4. What's I? And that particular relationship indeed did satisfy the passive sign convention. The current was going into the positive terminal, So we have a positive R times I. That's now 8 volts. What is our drink? What's V sub 8? R times I. It should, since the resistor is twice and the current's the same, the voltage drop should be twice what we just calculated, and it is. And it's 16 in both places. What did we calculate for the total drop across the source, the current source? 40. And that should be the same as what we've just dropped across all the resistors. 8, 16, and 16. 40. So we're looking consistent. Let's now find I sub 2. That was the current over here, I think. Wasn't that I sub 2? And here was our 12 ohm, and here was our 6 ohm. What did we just calculate? Anything to help us find I sub 2? We just found this voltage drop, V sub 4, and that was 8 volts, wasn't it? That voltage drop was across those two resistors. And now we're just pulling those two resistors, we're separating them out to identify the individual currents, and in particular the one current that was asked for, and that was I sub 2. And now we just use our voltage current relationship for a resistor. I sub 2 is now our voltage divided by the resistance, 2/3 of an amp. What if we would have come up with 3 amps?
Something went wrong.
Something went wrong, didn't it? If you came, what? You would get really rich. If you started with 2 amps and you come up with 3 amps, you could sell it, right? And get really rich. There we go, entrepreneur. Or you could be a realist and say something's wrong. You're expecting something less than 2. So what would you guess is flowing through the 6 ohm resistor, although we were not asked for that? The rest of the current. Just like Paul Harvey and the rest of the story, here's the rest of the current. Sorry. We started with 2. We got rid of 2/3 through the 12. And how much did we lose or have passed through the 6? 4/3. Twice as much as what was going in the 12 ohm. Does that seem to make sense? These are resistors, remember. They're resisting current. The bigger the resistor, the less current flowing. So you would expect 12 ohms to be carrying less current than the 6 ohm if they're both with the same voltage. And in particular, half as much. And that seems to make sense, and that's what we just calculated. But all we were asked for is I sub 2. What about on the other side? I sub 1, bless you. Here we had on the left-hand side the following picture. This one was 12 ohms. This was 24 ohms. And I sub 1 was there, wasn't it? Do we have enough information to solve this circuit or solve this sub-problem within the problem? We know V sub 8, don't we? V sub 8 was this voltage, wasn't it? And that was it 16 volts? What's I sub 1? I1 is actually going in, so if that's confusing you, I would just say, well, you know what? That particular spot electrically is the same as that spot. So there's my positive. And this spot electrically is right there. There's my minus. The I1 is going into the positive terminal of that resistor before it goes into the resistor itself. So V8 is equal to 12 times I sub 1. Let's solve for I sub 1. I sub 1 is V8 divided by 12. Is that right? Yes or no? How much is flowing in the 24 ohm? More or less than 4/3? Less. It should be half, right? And it is. Because we still should have 2 amps flowing through those two in combination, because that's what was flowing through the whole thing. Questions on that? Let's look at the next topic, which is really what we just talked about. Voltage divider formulas and current dividers. We just experienced current dividers. We saw how if a current of 2 amps is going into 2 resistors that are in parallel, how they divide, how that current divides among those two. In this case, the resistors were related in a nice manner. They were basically 1 and 2, or multiples of each other, a factor of 2 different. And that made the math or the thinking a little easier. Let's look at the first piece first, which is the voltage divider. Suppose we have the following circuit. And I want to know, what is this voltage V sub 1? Here's where your code number comes into play. I want you to take out a piece of paper that you're going to turn in, write your code number on it, and give me a formula for V sub 1 in terms of, oh, I forgot my code number. You didn't get that tattooed somewhere? Please don't do that. But I hope you remember your code number. If you do not remember your code number, you can write your name on it. But I want you to find a formula or an equation for V sub 1 in terms of R1, R2, R3, R4, and V sub S. What is a formula for V sub 1 in terms of the R sub i's and V sub s? And this is an individual assignment, no teamwork. I want to see if what we've talked about has made enough sense for you to make the next jump.
Before we put our code number, if we know what it is.
If you know what it is, you only have to put your code number. That's easier for me because I'm going to have a spreadsheet with the code numbers in it, and that's all it's going to have in it because I don't want to associate a wrong or a right answer with any one person at this point. I'll keep that all summed up, and at the end of the semester, I'll correlate your passport, which has your code number and your name, and then I'll say, okay, Johnny gets this for class participation. Does that make sense? So it's much easier if you remember your code number and that's what you put on your paper. Otherwise, I have to somehow open up multiple spreadsheets or different sheets, and I'm not real good with Excel. No, I'm okay with Excel. Question?
What's the probability that we have the same code number? One person.
If you have the same code number, if you think you have a common code number, right now I haven't verified whether I'm sure there is. So why don't you put your initials underneath your code number? Thank you. And hopefully you do not have the same code number and same 3 initials, or 4 initials, depending on your name, or 5, as your classmates, 150. So yes, I'm sure there is going to be similar code numbers, and I need to somehow get those sorted out.
I don't know myself yet. I didn't know what was given.
I'm going to, when you're finished, have you probably turn those upside down and pass those to your right. Except if you're on the west, you'll pass those to your left. Is everyone going to have an answer in the next 2 minutes? I'm going to assume that well, never mind.